All right, hello and welcome to some new slides. These are on a topic called recursion, and unfortunately I get to tell you that this is perhaps the hardest topic in this class. So definitely pay some extra attention. It's either recursion or pointers, depends on the student who thinks which topic is harder, but recursion wins a lot of the time. So the idea of recursion is finding a problem inside of itself. So there's a lot of memes to go along with it, and there's a lot of cool pictures to go along with it, like here's the problem inside of itself getting smaller. Same with the Russian stacking dolls. Here's the same doll, which goes inside of itself and it gets smaller. And even this cool, I think it's a tea manufacturer. They, like their logo involves the tea tin inside of itself, and there's the woman holding the tea tin inside of that forever and ever. So those are the kind of patterns that we'll see with recursive problems. And they will be fun to solve, though. I can promise you some interesting stuff for these slides. And it is fun once you get it. So let's get ourselves to that point. Okay, so let's begin and talk about recursion. So what we know how to do is iterate right now. We solve repetitive problems using iteration right now. And iteration is the opposite of recursion. Both of them solve repetitive things, but the way that they do it is completely different. So right now we know how to iterate through problems and solve them that way. So you know how to make like a for loop. For int I equals 0. That's iteration. Using loops is iteration. I is less than 42, I plus plus, and then you solve your repetitive problem inside of the loop body. Okay, so yeah, iteration or iterative solutions, that means you're using loops. So you got your while, you got your for. Recursion is when you loop without using loops. So without a while or without a for, it's very weird to think about, I know, but I will show you that there is a third option. All right, so let me show you just the basic idea of what recursion means. The standard example that everyone gives is the factorial problem, okay? Recursion, here's the definition, by the way. Recursion is when you solve a problem using smaller versions of itself. So you find the problem inside of itself, solve the smaller pieces first, and then you build up the answer, okay? So you find smaller versions of the same problem, and you build up that bigger answer to the original problem using the smaller version. Okay? So I promise this is going to make sense with an example. The example is factorial. Factorial is a recursive problem. You can solve it recursively. So let's figure out how. So think about it. What is factorial, by the way? Let's just get ourselves on the same page. If I ask you what 5 factorial is, you know that that is 5 times 4 times 3 times 2 times 1, right? That is what 5 factorial is. And I claim that factorial is a recursive problem, which means you can find a smaller factorial inside of itself. Okay? What does that mean? Can you find, take a second, pause the video and try it. Can you find the smaller factorial inside of 5 factorial? So I claim that because it's a recursive problem, there's a smaller factorial problem inside of 5 factorial. Okay? So try it, see if you can find it, and then we'll talk about it. Okay? So that's what factorial is. That's 5 factorial. Do you see the smaller factorial inside of this one? Well, that might be a trick question because there are a bunch of smaller factorials. Like here's 3 factorial, right? Here's 3 factorial, and here's 4 factorial. 4 factorial. There's 2 factorial. There's 1 factorial. They're all there. But usually we care about the next smaller one. So isn't that cool? 5 factorial can be broken down into 5 times a smaller factorial. Woohoo! That's the key. Noticing that idea, noticing a problem inside of itself should make recursion lights go off in your brain. Okay, so 5 factorial could be defined to be 5 times 4 factorial. Okay, and this is a common pattern. All right, let's keep on going with that pattern because, yeah, 5 factorial is 5 times 4 factorial, but you can do the same for 4 factorial, can't you? 4 factorial is 4 times 3 factorial. Oh shoot, that's interesting. So let's generalize that because we just noticed that, right? 5 factorial equals 5 times 4 factorial. But what is 4 factorial? But, well, that's still 4 times 3 times 2 times 1, right? And what do you know? That's 3 factorial sitting right there. 3 factorial. Crazy. So, yeah. 4 factorial is really equal to 4 times 3 factorial then. But what's 3 factorial? 3 factorial is 3 times 2 factorial, following the same pattern. What's 2 factorial? It's 2 times 1 factorial. What's 1 factorial but 1 times 0 factorial, which is actually defined to be 1, by the way. But you also are going to have to figure out where to stop. So we'll come back to that idea. But this is a pattern, right? So in general, n factorial is equal to n times n minus 1 factorial. Isn't that neat? So this is called the recursive case for the problem. This is where you're using that smaller answer to build up the bigger solution. I hope that makes enough sense. Do yell at me if it does not. This is called a recursive case. So here is n factorial. It's defined in terms of n minus 1 factorial. We just noticed that pattern. Okay? So yeah, this is the recursive case. You're using that smaller subproblem. You're using the smaller factorial to build up the bigger factorial, the original n factorial. Okay? Now, the issue with this is you can't follow this pattern until the end of time, right? Because eventually you're going to get to, all right, what's 1 factorial? Follow the same pattern. That's 1 times 0 factorial. What's 0 factorial? Oh, following the same pattern, it's 0 times negative 1 factorial, which is always 0, so that's going to make the whole thing 0. We definitely don't want to get this far, right? We should have stopped sooner. So you can't always follow the recursive cases rule. So we need to figure out where's the stopping condition. When does the problem get so small that we immediately know the answer? And so you could choose 0 factorial to be your stopping condition. It is defined to be 1, by the way. But let's just define it to be 1 factorial. Just say, okay, if you ask me for 1 factorial, I immediately know the answer. The answer is 1. I don't have to find a smaller factorial for you. Okay? So that's called a base case. A base case is a stopping condition for a recursive problem, when you don't want to follow that recursive rule anymore. So this is a good stopping place. So that's the second step. That's the next thing that you have to notice when you're solving a recursive problem, when you stop. And so we'll just say, okay, you ask me for 1 factorial ever. I immediately know the answer. 1 factorial, let's just define it to be 1, call it a day. So that is my answer. Okay? This is called the base case. So together, recursive case and base case, they give you a way to solve the problem for any value of n. That makes sense, at least. Okay? So with these 2 rules, we can solve the factorial problem. Are you ready? So we just noticed the following. So we got the base case for factorial. When do I know immediately the answer? So that's 1 factorial. Define it to be 1. And then the recursive rule, recursive case, give me some other number than 1. I know that that number factorial is equal to itself times it minus 1 factorial. N factorial equals n times n minus 1 factorial. That's what we noticed. And so we can use these 2 rules to solve the problem for our original 5 factorial, for example. So this is going to unfold the rule, right? What's 5 factorial? Follow the recursive case. It's 5 times 4 factorial. What's this? 4 times 3 factorial. What's this? 3 times 2 factorial. Keep on following the recursive case rule as long as I can. What's this? 2 times 1 factorial. What's this? I immediately know the answer because it's the base case. 1. And so we finally got to an answer, and then we can keep on shoving that answer back up the chain, okay? So yeah, my answer was 1. Hey, we can use that now. I know what 1 factorial is. I was told it was 1. I'll multiply 2 by it, and that's the result for 2 factorial. Give that back to whoever asked for it. You see how this is going to unwind? So now 2 factorial we know is 2, so we'll multiply 3 by that to get 3 factorial, and give that back to whoever was asking for 3 factorial. And so then we get back 6. And then that's 3 factorial. We can use that to multiply by 4 to get 4 factorial, and give that answer to whoever was asking for 4 factorial. So I'll take the 6, which was 3 factorial, multiply it by 4, and now I get 24 back. That was what 4 factorial should be. And then finally, we multiply that by 5, because we wanted the answer to 5 factorial. That was 5 times whatever 4 factorial was. I just figured out through a long process what 4 factorial was. It's 24. Multiply that by 5, and the original answer that I was looking for is 120. Okay? That's how we do it. And so there are some numbers that this doesn't work for, right? Like these rules won't work for -1 factorial. There are some things that still don't work, but this These are rules that work for every normal number that you might want to take the factorial of. Okay? We can like disallow this with an if statement in our code. So let's make this happen. Let's solve the factorial problem in this same way, in this recursive way, in code now. Okay, let me show you how this translates to code. These two rules, the base case and the recursive case. Here is the idea. So, well, usually when we're solving a problem, we're going to write a function to give back the answer. So let's make a recursive factorial function, right? That's the goal. So we're going to say like int fact. It takes some number n that we want to find the factorial of, and then we got to give some fancy body. And so a recursive function, therefore, if it's trying to ask for smaller factorials, it's going to call itself. That's weird. That should make you feel uneasy. But this is totally normal for recursion. A recursive function is a function that calls itself because it needs the smaller answers. So it calls itself on a smaller version of the same problem. So we're going to be calling, we're going to compute n times n minus 1 factorial. We're going to call fact of n minus 1. We're going to call the function that we're defining in its definition. Crazy, but it's going to work. Okay, so inside, here's our recursive case. Return n times whatever the n minus 1 factorial is. We're just translating this rule. This is n minus 1 factorial, so call ourselves. Find that answer, please. And then the base case is, okay, when n is 1, immediately the answer for 1 factorial is 1. Okay? So with these two rules, we can make a function that has no loops, but technically does loop. All right? That's crazy. So you can totally do this same answer. You can compute this answer, of course, using loops, as you know how to do already. But now we have a third option, another way to do it. Okay? Don't have to use while, don't have to use for. And sometimes, I promise, eventually you'll get here, that it is easier to think about a problem recursively and to not use normal while and for loops a lot of the time. Okay? And you will get experience with that in detail, if not in this class, in CSCI 41. Okay? So, yeah, let me program this for you. I think we're ready. So let me just program this for you and prove that it's going to do the right thing. So I want to do something like, I'm going to output the factorial of 5. And here's how you do it recursively. So normal function, it's called fact, computes the factorial. Yeah. Of whatever n it's being given, and so we have to figure out if we're in the base case or the recursive case. If n is 1, that means we're in the base case. The answer to 1 factorial is 1 itself. Otherwise, we're in the recursive case. The factorial of any number n is n times n minus 1 factorial. See that? I'm just translating it straight to code, those rules that we came up with. And surprisingly, this is going to work. Oops. Boop. And the answer is, in fact, 120. This is really computing the factorial, and it works. It works just fine. Let me show you why. If this is not clear enough yet, like why is this actually computing the answer correctly? Let me show you what's going on. It's really this kind of chain reaction, just with function calls and function returns. So let me show you this to you, okay? A stack diagram is the thing we need here. So yeah, the function call stack, or the runtime stack, it looks really cool the way that recursive functions are running. So remember what we were doing here. We were in main, and then main was trying to compute factorial of 5 so that it could print out the answer. So main calls fact of 5. So that's what's going on. And fact of 5 is going to call fact of 4, right? Because it's in the recursive case. Here, n is 5. Because we called it fact of 5, we jump up here with n being 5. And we hit this case because n is not 1. So we need to multiply 5 by fact of 4. n minus 1 is 4 in this case. So we need to go off and compute this before we're ready to multiply our 5. Yeah, so fact of 5 is going to call fact of 4. It needs to know the answer for 4 factorial so that it can multiply its 5 by that. Yeah. And then similarly, fact of 4 is going to be like, okay, now we're up here with n being 4 again. It's another call to the same function. But now n is 4, and we need to go to the recursive case again. Return 4 times 3 factorial. So we need to go off and compute, hey, what's 3 factorial? So we can then finally give back the answer for 4 factorial, so that we can then finally give back the answer for 5 factorial. So all of these functions, they're calling themselves. No function call has returned yet. They're all waiting right here on this call to the subproblem. Okay? That's the key. So fact of 3, again, recursive case, it's going to ask for fact of 2, so that it can multiply its 3 by that and give back its answer. Fact of 2 is going to ask for fact of 1 in the same way, because you're going to go up here with n being 2, and then you're going to try and multiply 2 by fact of 1. We need to go off and make another call to compute that, though. And so, yeah. Finally, we call fact of 1, and it's going to return 1 back to whoever called it, because that was the base case. It's like, all right, n is 1. Cool, return 1. And so now we're back here. Fact of 2, remember, was sitting on this line with n being 2, so it can multiply its 2 by the answer that it just got back. The answer was 1. So 2 times 1, 2. Hey, do you see how this is working? And fact of 3, again, was waiting for fact of 2. It was waiting right here for fact of 2, with n being 3. So it multiplies its 3 by fact of 2 that it now has the answer for. It just got it back. And gives back 6 to whoever called it. And it was fact of 4 who was waiting on fact of 3 right here again to multiply its 4 by fact of 3 to give back 24. To whoever called it, which was fact of 5, which was waiting right here again to multiply its 5 by fact of 4. Okay? Finally got the answer. And we're here. And by the way, every time this returns, these stack frames go away, right? So now we're back in main, and fact of 5 finally returned back its answer of 120. So once you get to the top here, the stack starts unwinding, okay? Popping stuff off to give back answers to the people who called those functions, okay? So that is how it's working, and then finally main gets back 120 and prints it out, okay? Do yell at me if that is not making enough sense. This is the reason the factorial function worked recursively. Okay? Now, I think we can agree that it's going to do the right thing now, and I've shown you why, but maybe it's still a bit fuzzy. Like, why in the world am I allowed to do this? Like, call myself. That seems really weird. That makes me feel uneasy. So let me try and give you a proof for why recursion is always going to work. If you solve a problem in this way, it's always going to work properly. It's going to seem unintuitive, I promise. You'll have to wait until CSCI 26 to get a better grasp of why this is happening, but I'll at least give you the short version of what's going on here. So recursion works regardless of the problem. So let's pretend we have some kind of problem. It's up in the air. It's some black box. Our problem is called P, let's say. It could be factorial, it could be something else that can be solved recursively. So if our problem is called P, what does the base case and the recursive case really look like? What do those mean? Okay, so the base case is something like, hey, I know the answer to P of 0. So like I have that at my disposal. You ask me for the problem at some small size, I can give you back the answer immediately. So that's what the base case is doing. It's saying, I know how to solve the smallest possible problem for this problem P. And then the recursive case is doing this kind of thing. It's saying, you give me the answer to one smaller of a problem, and I can give you the answer to the next bigger problem. So does that make sense? So solve me the problem. I can give you, you give me the answer to a size k version of this problem P. I can then build the answer to a size k plus 1 problem based on that smaller solution. So it's like, you give me P of k, I'll give you P of k plus 1. Okay? So that's what you get with recursion. You have these two answers, those two cases. You know how to solve the base case and the recursive case. And those two rules combined can solve P of n for every n greater than or equal to 0. And I'm going to try and show you why. Okay, so here's what's happening. You immediately know the answer to P of 0, right? So you can just be like, I know P of 0. I claim that. That's what the base case tells me. But then, how do I solve bigger versions of this problem for P of 1, P of 2, P of 3? I can then start using the recursive rule. Set k to 0, like this is saying, if you gave me a size k problem, I can give you a size k plus 1 problem. That's what the recursive rule does. oh, I have a size 0 problem. That means I can plug it into this and get the answer to a size 1 problem. And now suddenly I have the answer to the problem that is 1 bigger. Okay? And now I can use this, plug it into the recursive rule, set k to be 1. It's like, okay, you give me a size 1 problem. This rule knows how to give me a size 2 answer. Oh man. So that's how you build up P of 2. And you can use P of 2 with the recursive rule again to build P of 3. You set k to 2. Be like, all right, if you give me the answer to a size 2 version of the problem, oh, I've built that, I have it, then I know how to build the size 3 version of the problem. Does that make sense? And then you can just build up that answer for as big of a number n as you need. And the idea with recursion is it's kind of computing that answer backwards. It's like going downwards to that smallest base case, so it's going this way. And then it's using this rule to build up the answer to the original problem of size n that you were asking for. That is what recursion is doing. Okay? So that's why it works. That's why you can solve any version of the problem with just a base case and a recursive case. I hope that makes a bit more sense now. And it's definitely the recursive case that is the harder one to wrap your mind around. I think we can all agree with that. There's kind of a bit of magic going on. Like, the reason this works is that you get to assume that this call to the smaller version of the problem, that's called a recursive call, by the way. This right here, fact of n minus 1, that's called a recursive call. I'm calling myself. So that you get to assume that recursive call works correctly, don't you? You don't have to like check the answer. You just get to assume that it's going to work, assume that you have the answer to this. As long as you build up the answer to the size 1 more problem correctly, it will be correct. Okay, and this is something that I can't really prove to you right now, but it is the truth. Okay, as long as you build up the larger answer correctly, you get to assume that this really did compute factorial of n minus 1. You don't have to worry about it anymore. Just assume it's giving you the right answer, build up the larger problem's answer correctly, and that smaller call really will have worked, okay? Because it's going to hit that base case. It's going to go down. It's going to start building itself up. It will have that smaller answer. As long as you build up the next answer correctly, it's going to keep following that rule to get to whatever version of the problem you were asking for. P of 3, P of 4, P of 5, okay? So this is how I want you to think when you're implementing the recursive rule. Just assume that when you make the recursive call on the smaller problem, assume it's going to work, and then build up that answer correctly, okay? Because it will eventually work. It's going to get down to the base case and use your recursive rule. It will have the right answer. Just keep on building the next right answer using that. Okay, so that's a lot of words. With more examples, though, we'll get more practice and we'll be more confident with recursion. Okay, so here's another problem, another smaller, easier problem maybe that is recursive. So power computation. Okay, I don't know why I said this. Let's get rid of that. So power computation, I claim, is a recursive problem. So computing 2.5 to the power of 5, for example, that's a recursive problem, which means there's a smaller power computation inside of that one. So take this example, see if you can find a smaller power computation. Okay, so pause the video, give it a try. Did you see it? The idea is to always write it out. What's 2.5 to the 5 for this silly example? Well, that's 2.5 times 2.5 times 2.5. Oops, I'm drawing dots in wrong places. Times 2.5 times 2.5, right? Do you see a smaller power computation? Oh, here's one. Here's the next smaller one. It's 2.5 to the 4th, right? And like here's 2.5 cubed. Do you see how a power computation is hidden inside of a power computation? And then there's like 2.5 squared, 2.5 to the 1. Those all exist. Usually we care about the next smaller one, though. Okay? So that will give us a recursive rule. We generalize now. Okay? We're going to make a function called pow x and y. So it should compute x to the power of y. And you just found a smaller power computation inside of an existing one. So like you want to calculate 2 to the 4. That's 2 times 2 times 2 times 2. And what do you know? That's 2 cubed. Yeah? But what is that? Well, it's 2 cubed, but 2 times 2 times 2. Oh, there's 2 squared. Not factorial. There's 2 squared hidden inside of that. So generalizing this, you can come up with a recursive case and a base case. What's our recursive case? Well, it looks like any number m to the power n, that's equal to, just generalize this case, it's equal to, well, that first number, so m, times the one smaller power computation, so m to the power of n minus 1. That's the recursive rule. You see how it's getting smaller? That's the idea. And then we need to think of a base case. Like, when are we done with the answer? Like, when do we immediately know the answer regardless of the input? And a good stopping condition, if you write it on out, it's like, okay, 2 squared is equal to 2 times 2. That's, okay, that's 2 to the 1. And then 2 to the 1 is equal to 2 times 2 to the 0, following the recursive case rule. 2 to the 0, what's that? Well, that's just 1. We can just stop there. So any number to the 0th power is 1. That's our answer. So that's a good base case. Okay? That'll stop our power computation. Okay? And so, yeah, what the recursive case is doing, it's finding that smaller power computation and using it to build up the bigger power computation. Okay? And we get to assume when we're coding this up that, like, this smaller recursive call is really going to get that answer correctly. As long as we build up the answer, the original thing will be correct. The original input will be correct. Okay, so let's code this up, and then I will draw you another stack diagram. Okay. pow.cpp. So I don't know, see out. Let's do 2 to the 5 for a reason. So that should compute 2 to the power of 5. I guess technically this could be double. It could return a double. It could take a double m, but the power needs to be an integer. We can't do fractional things here. Okay, so we can technically take a double as the thing that we're taking the power of, power 2, but the power itself must be an integer. Okay, it's got to be a whole number. So our goal is to returns m to the power of n. Okay, so we need to, again, figure out if we're in the base case or the recursive case, because that'll tell us which rule to follow. So if we're trying to take something to the 0th power, n is 0. Then we return 1. Anything to the 0th power is 1. Okay? Else, and that was the base case. Else we're in the recursive case, and m to the n is equal to m times m to the n minus 1, right? That's how that's going to work. So return m times, well, how do I compute m to the n minus 1? You just use the magic of recursion and call your own function. Assume that this smaller call is going to work. As long as you build up the answer correctly, it will have worked. Okay, so that's the answer there. 2 to the power of 5. Let's go and check and see what that is. 2, 4, 8, 16. Looks like it's 32, according to my fingers. And yes, so that is going to do the right thing. It's going to compute 32 correctly. So that's pow. All right, so let me show you why this is working. Computing pow of 2 to the 5. Pow of 2 comma 5. Why is that computing 32 properly? Why is it really taking 2 to the 5th power? So again, in main, we called pow on 2 to the 5 so that we can print it out. Pow 2 comma 5. So that was this call, and then we jumped up here with m being 2 and n being 5. Okay, so n is not 0, we're not in the base case, so we're in the recursive case. So we need to multiply our m, which is 2, times 2 to the 4th power. 2 and n minus 1. If n was 5, then now it's 4. So we need to go off and compute a subproblem's answer, power of 2 to the 4. Okay? And again, recursive rule, what's 2 to the 4th power but 2 times 2 to the 3rd power? We need that answer before we can complete anything. So none of the pow function calls have returned yet. They're all sitting right here again. They're waiting on this call to give back an answer so that it can multiply its m by that answer and give it back. Okay? So pow 2 to the 3, going to call pow 2 squared. This is going to call pow on 2 and 1. And remember, this is m, this is n. These are all separate function calls. They all have their own values of m and n. Like here is, like down here, this is m is 2 and n is 1 for this particular call. Okay, but the rest, like this here has m being 2 and n being 1. It's a completely separate variable. Remember that these are all different scopes, different stack frames. They all have their own variables. Okay, so pow of 2 to the 1, again, n's not 0. It'll try and compute 2 times 2 to the 0. So it's got to go off and compute pow of 2 and 0. And then finally, that's the base case. It can give back its answer of 1. Okay, so bam, my answer is 1. Thank you. Pow of 2 to the 1 was sitting right here waiting on pow of 2 to the 0. It can multiply its 2 by that answer and give it back. Okay, so it gives back 2, multiplies 2 by this answer. And that's what we give back to pow of 2 squared, because it was waiting on pow of 2 to the 1. Answer is 2. It can then multiply its 2 by that answer, give it back to whoever called it. So yes, 2 squared, the answer is 4. And so as they return, they pop themselves off the stack. And then 2 cubed was waiting on that answer for 2 squared, so it could multiply it by 2. So it gives back 4 times 2 is 8. And again, 2 to the 4th was waiting on this line again to multiply its 2 by 2 cubed. Answer is 8. So we give back 2 times that, which is 16. And we're done. Back to pow of 2 and 5. That is finally what we really wanted the answer for. Again, it was waiting right here on 2 to the 4th. It got the answer back. The answer was 16. It could multiply its 2 by that and give it back. Cool. The answer was 32, and that's why main is printing 32. Okay? So that is the stack diagram. Hopefully that makes a bit more sense why it's doing what it's doing. But it's all a matter of examples, I promise. The more examples you see, the more natural this will seem. Okay? But that is recursion. That's another recursive problem, computing the power of something to something else. Okay? So now, I need to tell you some bad news. Okay? You can have a new kind of problem when you have a recursive solution. So remember how you could totally have infinite loops when you had iterative solutions, when you were using while and for? You can totally still have infinite loops with recursion because it's still doing some kind of looping process. It's just a bit uglier. Like the program is going to crash because of the way that this is working. If you repeatedly loop, that means you're repeatedly making function calls, and each function call takes up space on the stack. You don't have infinite memory, right? So eventually, your stack is going to run out of memory, and that's called a stack overflow, okay? When your stack gets so big that you run out of memory. Because remember that the stack is competing for space. Like here are all your function calls, here's your stack. Calling functions, it's growing that way. And then the heap, all of your dynamically allocated memory, is growing down this way. If you call more functions, it's going to eventually like cross. You're going to run out of space. Because remember that each stack frame, every time you call a function, it's got to take up memory because it needs to store all the parameters, all the local variables. They're all separate, right? All separate local variables for each function call. It also needs to remember who it's returning to. That all takes memory. Okay? So that is something that could go wrong now. And the easiest way to have something go wrong, the easiest way to have a stack overflow, is to forget the base case. Okay? So that is going to make sure that your program never stops, right? It's never going to get to a case that's going to give back a final answer. It's going to keep on trying to compute subproblems answers. Let me show that to you. And now you know why that, Now you know why the website is called Stack Overflow. All right, so let's just steal everything from Factorial. Here's version 1 of a problem. I guess I didn't need to do any of that. Okay, so if I forget the base case, oh no, we forgot the base case. Do you see how this will never finally give back an answer? It's like, all right, it's always going to try and compute a smaller problem. It's always going to keep going, no matter what n you give it. It's going to like, okay, I'm going to keep on going as long as time lets me. as long as my memory lets me, okay? So this is going to try and compute fact of 4, fact of 3, fact of 2, fact of 1, fact of 0, fact of n minus 1, or negative 1, fact of negative 2, until the end of time, because there's no base case, okay? So let me show you what's going to happen here. Stack Overflow. And so it's going to keep on calling fact and run out of memory. And when you run out of memory, you try and access memory that isn't yours anymore because you don't have that many addresses. That gives you a seg fault, okay? But really, it was a stack overflow because we kept calling the same function. We built a tower as tall as we could of stack frames, and eventually we didn't have enough space, okay? So that was the problem. The next easiest way to have a stack overflow is to forget that in your recursive case, you need to make progress. You need to go towards the base case, otherwise you're never going to get there. You need to solve a smaller problem. So here is a correct mathematical statement, but incorrect code, right? Trying to say that, oh yeah, the answer to n factorial, oh, it's n factorial. So you're calling yourself with the same parameter. You're never going to get towards the base case, okay? So this is Stack Overflow 1, issue 1, or I don't know, Stack Overflow 1, and then let's do it again. Let's have a different version of the fact function. This is Stacked Overflow 2. So I'll comment out all this. Oops. How do I want to do this, I guess? Just comment everything out then. I'll use a multi-line comment. So maybe you remembered the base case. So let's steal the correct version of fact again. Maybe you remembered the base case, but you just never got there. So what is the factorial of n but the factorial of n? So it's like, okay, what's fact 5? Well, it's whatever fact of 5 is. Let's go off and call fact of 5 again. Oh, that's going to call fact of 5 some more until the end of time. Okay? So you're never going to get towards the base case. So that is another problem. That will give us another stack overflow. Boop. And so another stake fault because we kept calling fact of 5 a million times. Okay? So study these two cases. Those are two common ways to run into trouble with recursive functions. Okay? That's called the stack overflow. And then for my final example for this lecture, I want to talk about the Fibonacci sequence, which is a very fun one. Definitely go look it up on Wikipedia. It's really cool looking. Here is the Fibonacci sequence. It is very common in like nature. Definitely look up the Wikipedia page. There's a bunch of pictures of like ferns and things. Like the Fibonacci sequence, it comes up a lot in real life, and it approaches, like the ratio between elements of the Fibonacci sequence as you get pretty far into it, approaches a special number called phi. Okay, so definitely look that up. But here is the Fibonacci sequence. That's all I need you to know right now. It starts with 0. Some people think that it's like the first two sequence elements are 0 and 1. Other people think that the first two sequence elements are 1 and 1. Is not a big deal. Either one of those works. Let's just assume in our case that the first two elements of the Fibonacci sequence are 0 and 1. And then here's how you compute the next value in the sequence. You take the two previous values, you sum them up, you add them together, and that gives you the next one. So what is 0 plus 1? You add them together, that is just 1. And that will give you the next element. So you just keep on following that process. It's like the sum of your two previous elements. Add them together, 1 plus 1, that's 2. So that's the next element of the Fibonacci sequence. What's 1 plus 2? It's 3. What's 3 plus 2? It's 5. What's 5 plus 3? It's 8. 13, on and on and on. Okay, so that's the Fibonacci sequence, and that's how you calculate it. This is a recursive problem. How do you figure out the nth value, the nth number in the Fibonacci sequence? Let's say that this is like the 0th one. This is the 1th element of the Fibonacci sequence. Number 2, number 3, number 4, number 5, number 6, number 7. So let's say somebody's asking us for the nth Fibonacci number. Okay? We'd like to make a function called fib of n to calculate the nth Fibonacci number. So for example, if someone says, what's fib of 7? We got to give back 13. What's fib of 6? We got to give back 8. Stuff like that. So this is the Fibonacci sequence. You actually need two base cases, but let's do the recursive case first because that's easier. That's easier to notice. This is a recursive problem. You can solve for the nth element of a Fibonacci sequence in terms of smaller elements of the Fibonacci sequence, can't you? Let me show this to you. So, okay, I'm asked for fib of n. I want the nth element of the Fibonacci sequence. This is a recursive problem because, like, let's say they're asking us for Fibonacci of 6. What's fib of 6? That's equal to fib of 4, right? Fib of 4 plus fib of 5. And that's always true. So what is the Fibonacci, what's the nth element of the sequence? Well, it's whatever the n minus 1th element is, plus whatever the n minus 2th element is. Isn't that interesting? So you got to call yourself twice, and these are smaller answers. Those are smaller inputs, and so it will make progress towards the base case. Isn't that so cool? So that is the recursive case. The base case is actually two separate cases. Let me show you why. The issue is, the reason you need two separate cases is because you don't immediately know the answer for the 0th element and the first element of the sequence. So fib of 0 and fib of 1, those can't be computed using previous elements because there aren't two previous elements for 0, and there's only one previous element for 1. There's no way to get to the other one. Okay? So you have to start it off somewhere, and because this is always needing two previous elements, if you don't have two previous elements, you just have to immediately say the answer. Okay? So that's why you have to say fib of 0, define it to be 0, that's a base case. Fib of 1, also define that to be a base case. Okay? So let me compute this for you. I guess let's code it up so that we're ready for next time. But I'm going to eventually show you that this implementation is actually really bad. Okay? So, but this is going to work. We calculate the recursive case. We notice we solve the problem in terms of smaller versions of itself to get to those smaller elements of the Fibonacci sequence. And then we notice when our stopping conditions were. Like, what's the smallest input for which I immediately know the answer to the Fibonacci sequence? When does the recursive rule not work anymore? Was another way of thinking about it. Okay? So those two rules, 3 cases total, I guess, give us Fibonacci. So we can ask for what was the 7th element of the Fibonacci sequence, and hopefully it's going to print 13 for us. So this is going to ask for the nth Fibonacci number. That's the nth element of the Fibonacci sequence. That's another way to say that. So, okay, now we need to first check the base cases. We need to figure out if we're in the base cases or the recursive case. Oops. So we have 2 separate base cases. If n is 0, then this is base case 1. Then we need to return 0. The 0th element of the 0th Fibonacci number is 0. Otherwise, if n is 1, that's the other base case. Fibonacci of 1, the 1th element of the Fibonacci sequence, I guess, is 1 itself, and then the recursion can take over, because then we have 2 previous elements always for anything bigger. So if we're in the recursive case, we give back, well, the answer for the nth Fibonacci number is, well, it's the sum of 1 Fibonacci number ago plus 2 Fibonacci numbers ago. That's this. Just assume this works. Assume we have those values at our disposal. Add them together. That's the answer. I don't have to think any further. So it's like looping without having to think about having to loop. It's really cool. All right, and so the answer is 13, and I want to stop and show you, or maybe just hint at why this is a horrible implementation, okay? The issue lies with the 2 recursive calls that we need to make each time. So fib of n minus 1 is going to go off and compute a bunch of stuff, and fib of n minus 2, knowing nothing about this work that was done by fib of n minus 1, is going to go off and also compute a bunch of stuff. So it's like going to the way that we call things, it's going to be like, all right, it's going to branch into 2, make 2 recursive calls. And for the smaller inputs, it's also going to branch into 2 and make 2 recursive calls. So it's going to get really wide. It's going to make a lot of computational stuff to do for itself. Okay? So that's one issue. The other issue is this call knows nothing about the work. Like, this call knows nothing about the work being done by this first call. And they are going to overlap. What this one's asking for is going to overlap with a lot of the things that this one's asking for. And so it's going to recompute answers. Okay? So I'm going to explain that in full, in a lot of detail next time, but I want to get you thinking right now. So this is actually a horrible implementation. I can prove that to you, though, next time. So you're going to have to wait. So I will see you in the next lecture, and we'll talk about why this implementation sucks. So I'll see you then.